In this video, we're going to start a section on area moments of inertia of composite areas. By composite areas, I mean an area that's made up of several subareas. For example, this is an example problem that will work a little bit later, but this is a shape that's made up of a rectangle, a triangle, a half circle, and has a circular hole. So what we're going to do is we're going to apply the formulas for the area moments of inertia of each of these shapes and use the parallel axis theorem to determine Ix and Iy for this composite shape. But first, I'm going to go back and derive the parallel axis theorem one more time and present it with a general formula that I like to use for composite shapes. And then we're going to go from there. So deriving the parallel axis theorem for an area where we know a centroidal moment of inertia, and we want to find a moment of inertia about some other axis, we use the parallel axis theorem. So this is the derivation. I did it earlier, but I'm just going to review it quickly here. So if you have an area that has a centroid at C and centroidal axes x prime and y prime, it's located some distance from the y and the x-axis. And so the distance from the x-axis to x prime is dy. The distance from the y-axis to the y prime axis is dx. And if we identify a little element dA on the area, and dA is some distance y tilde from the x prime axis and x tilde from the y prime axis. If we want to find the moment of inertia around the x-axis of this area, what we can do is find the distance from the x-axis to our dA. And so we have dy plus y tilde, that quantity squared times dA. If we expand that term out, we get dy squared times the integral of dA plus 2 times dy times y tilde plus y tilde squared dA, and that's equal to Ix. But if you look at these guys term by term, so remember dy is a constant, so it can be brought out of the integral. So this third term is a dy squared times the integral of dA. Well, the integral of dA is just area times dy, which is the distance here. So an area times a dy squared. This term is 2 dy times the integral of y tilde dA. But this integral is the numerator of a centroid equation, and it's basically the moment of the area around the x prime axis. But the top of the area above that axis is a positive y dA. The area below that axis is a negative y dA. And so the entire integral becomes 0 for the entire area by definition for a centroidal axis. So this guy drops out. And then this guy is the integral over the area of y squared dA. Well, that's Ix prime about the x prime axis. And so finally, what you get is the area moment of inertia about the x-axis is equal to the moment of inertia around the x prime axis, or in other words, it's a centroidal I, plus the area times d squared. And that's about the x-axis. If you did the same thing about the y-axis, you would get Iy is equal to I bar y prime plus a dx squared. I like to generalize the formula by basically calling it I-axis is equal to I bar plus a d squared, because I bar implies the centroidal axis. And so to put y prime or an x prime in the subscript is redundant. And so this is, to me, the general way to write the formula. So if you have an area and you know it's centroidal I, and you seek his moment of inertia around some axis that's parallel to I bar, and it's a distance d, then I-axis is I bar plus a d squared. If you want around the y-axis, again, the I about the y is equal to I bar about the centroidal axis that's parallel to y plus the area times the distance squared from that vertical axis to the y-axis. So I like to generalize it this way. Finally, if we're dealing with a composite shape that's made up of multiple shapes, and you're looking for a moment of inertia around the x-axis of those composite shapes, then for each shape on the object, you're going to write an I bar plus an AD squared for that shape about that axis. And then you're going to add the I bar plus AD squared of another shape, and so on, for all of the different shapes of your composite area. And that's the IX or the IY for that. So that's basically what we're going to do in this short unit here, area moments of inertia for composite areas.